So I want to give or make a clarification about what I refer to as certain technical conditions that we need to invoke in order to work out the balance of energy in the form that was presented. Okay. So I'm going to title this clarification as boundary conditions on omega t. All right, here's the situation. We have the body, and so far, whenever we talked about applying traction boundary conditions, we always spoke in terms of a subset of the boundary that we denoted as partial of omega t sub t. Okay, and on this portion of the boundary, we always said that we have some traction specified, right? And though I'm drawing it at only one point, really the way we want to think about it is that there is a distribution of traction, right? So T is a traction field which is defined in that part of the boundary. Now this naturally brings up the question which I've been avoiding, and that question is, what about the rest of the boundary? Okay. For mechanics, and whether we're doing solid or fluid mechanics, it doesn't matter. But if we say that part of the boundary is where we're specifying the traction, you do need to have other conditions on the rest of the boundary. Okay? And so the remaining boundary subset, the complement of the traction boundary, is what we will denote as partial of omega t sub u. The u there reminds us of the displacement. Okay, and on this boundary subset, we have displacement boundary conditions specified. Okay, so on this part of the boundary, we may have u equals u bar. Okay, all right. So partial of omega t sub t is the traction boundary, right? And partial of omega sub t sub u is the displacement boundary. Right? On the traction boundary, we have T equals sigma n. All right, that's a boundary condition on the stress, which is one of the quantities that describes what's happening to the body. Okay, and on the displacement boundary, we have U, which is the displacement field, equals U bar, which is a given field. Okay. All right, so this is given, right? Likewise here, in the traction condition, what is given to us is T. What we have to determine is sigma, right? On the displacement boundary, what's given to us is U bar, and whereas U is the field that we're trying to determine inside the body. Okay, now what we also require is what we call dead loading. Okay, so we consider cases of dead loading, which essentially means that the boundary conditions are not changing in time. Okay, so we consider dead loading. Okay, where we're saying that U bar, let's say this, right? Right, we have this, and likewise the time derivative of the traction, and I realize this looks strange there because we finally have a collision between the two uses of t. Okay, but that is just a material time derivative of the traction. Okay, we're saying that this too is 0. Okay, right. So these are the conditions of dead loading that we have. We are essentially saying that, look, we have loading that's acting on the body, it's producing certain velocities and so on, but those conditions that we're applying on the body themselves are fixed in time. Okay? So what this lets us do is the following. Okay? So now we can equivalently, when we start out with the external power, right, when we say it is the body force dotted with the velocity dv plus integral over partial of omega t, t dotted with the velocity dA, we can pretty much without, we can actually add here the displacement boundary, okay, and here we can simply write this as sigma n dotted with v dA, okay. But here's what happens. On the displacement boundary, we have a displacement boundary condition, and we've required that displacement boundary condition is fixed with respect to time. What that means is that on this boundary, on the displacement boundary, the velocity, which we know is partial of u with respect to time, right? That is the definition of the velocity, right? It is equal to partial with respect to time of u bar, which we are requiring to be 0. Okay? Right? So we're really adding that second term in there, but it really does not do anything to our conditions. And then when we apply the Cauchy theorem, there we get that. Right? So essentially what we're saying is that we're basically applying our boundary conditions here on these two boundary subsets. Okay? Now, never mind the fact that the second integral is 0. What this lets us do is write out that as an integral over partial of omega t sigma n dot v. Okay? So the idea is we are including the work done on the displacement boundary, okay? And we're saying that, well, if we consider dead loading, that term is 0. Okay? All right? So we're really not adding anything to the body in addition to the external loads. Right? We're not adding any work coming in from the outside if v is equal to 0. Right, on the displacement boundary. Okay, and then we're able to combine both those boundaries, okay, in this form. And it's on this form that we then apply the divergence theorem. Okay, from the divergence theorem, this is equal to integral over omega t. Now we know that this becomes divergence of v dot sigma. dV. Okay? So this is what happens in the case of dead loading. Okay? All right. Now you may wonder, well, does this not work if you don't have dead loading? Okay? So even if you don't have dead loading, you can do exactly this, right? It is just that you would be, supposing we were to say that this condition v equals partial of u with respect to t is not equal to 0 on the boundary. You want to relax this requirement of dead loading on the displacement boundary, right? You can't quite relax it on the traction boundary, but you can relax it on the displacement boundary. And then what that lets us do is to observe that, well, yes, even without that condition, we're able to add this back in, right? And that if we were not equal to 0 on the displacement boundary, if this condition did not hold, right, the second integral would not vanish, okay? But then what we would be doing is also including the work done internally by the stresses on the specified displacement boundary, okay? And then we could still get to this to this form of the boundary term, and then go on to that using the divergence theorem, right? This is using the Gauss theorem, right? And from here we could proceed just as we did before. Okay, so these are just certain technical conditions which come in with the use of boundary conditions in the context of the balance of energy.